don't know. But when I crossed these tall plants, again I got the short plant here. So that means it was not mixed. It segregated. The traits were segregated and gave us the result when the condition was covered. Clear this part? So that is the thing. The alleles separate when the gametes are formed. That means the alleles separate. I will explain this one now. And alleles separate in equal proportions. So first thing is that it segregates. There is no mixture. And how it segregates? By the form of alleles. Now this one I will go with the chromosomes. Okay. In genetics, generally we denote schematic diagrams of chromosomes. Schematic diagrams means just this is a chromosome. Schematic diagrams we need to do sometimes for better understanding. When we are drawing this way, this represents autosomes. If you go to the little bit older classical genetics books, you will find in these symbols. When now not in your books, I don't know whether they don't follow these things, but it was almost a rule that when you need to draw autosomes, the autosomes are like this. And when you need to draw the sex chromosomes, it is like this. This means two X chromosomes, and this means X and Y. Okay, these are the symbolic representation of the chromosomes. Now we are talking about the autosomes part here. Okay. So this is the tall plant. I took the genes for tall plant is capital T, and for the short plant is small t. Okay. So the tall plant, it is pure tall. So like this. It is pure short. So like this. Okay. Now for the formation of gametes, what is happening here? We'll find two gametes from here, and we'll find two gametes from here by the process of meiosis. Okay. Now, if you think about that, alleles separate when gametes are formed. Is it the proof? Alleles separate when the gametes are formed. If I go through the meiosis, alleles separate. All the chromatids will separate. That means the alleles are separating there. So alleles separate when the gametes are formed. Clear? Now, as these two are the similar alleles, so I am taking just only one from here, only one from here. Okay? These are the same types. So the F1 will be like this. This is our F1 generation. And what will be the phenotype? Phenotype will be tall. So if we consider the phenotype tall, that means we don't know whether it is already segregated or not by the phenotype only. To prove that one, we need to go for the genotypes and go for the second generation, that is F2. So we have two plants of the same characteristics, hybrid plants in F1 generation, and these are the two. We are self-pollinating or something like that, self-fertilizing these two plants. So we will have one this chromosome and one this chromosome, right? This is one. Observe. One this chromosome and one this chromosome. One this chromosome and another this chromosome. and last one, these two. Right? This is tall, this is tall, this is tall, this is short. Clear? So the proportion is 3 tall, 1 short. 3:1. That is the proportion. Now there are two things. Alleles separate in equal proportions. Alleles separate in equal proportions. Two capital T, two small t's are here. Okay. In this case, if you consider 1, 2, 3, 4 capital T, 1, 2, 3, 4 small t, they separate in equal proportions. Okay, the law is proved right now. Segregation of alleles in equal proportion. Okay, clear this part? This one I will come later, the independent assortment. This is another example in your book. You will find this one, how the alleles are separating. What I draw there, that is the same thing here. But there are two things. If there is crossing over, that means the change in alleles in the chromosomes, that could occur, but they also separate in same proportion. We will get two capital R and two small r. Whether it's a crossover type, whether it's non-crossover type, that doesn't matter. Okay? Now, concept of dominance and recessive. So from Mendel's monohybrid cross, we got one law of segregation, and one concept of dominant and recessive. And these represent the concept of dominant and recessive. When there is hybrid, capital T gene is suppressing the character of small t, tall is suppressing the character of short. That means tall is dominant over short, short is recessive, and when the recessive characters are together in homozygous condition, only at that case they will show their phenotype, otherwise not. So tall is dominant and short is recessive. Another terminology or symbolic representation here, according to Mendel's process, when it is tall or dominant character, we generally do that character as capital. So tall is capital T. And the same thing, in case of short, we are not taking S, we are taking small t. It represents the recessive character of tall. Clear? This is a symbolic representation for any kind of genetic process. And this is for autosomal process, Mendelian process. When we will go to sex-linked one, that is a little bit different. Okay? So this is the thing here we got. Now the representation of these things by the Punnett square. Representation of these things, this is a little bit complicated, right? This is a little bit complicated. I can represent this one very easily by drawing a square. And that is called the Punnett square. It is not like that, it is a very big thing. It is just the representation of the whole thing. So let's go to here. So we are taking two hybrid plants. This is our F1 generation. Now we are taking all the gametes here. Male gametes and female gametes. So we are having two types of gametes. These represent male, square with arrow, circle with arrow, and these represent female. And we are talking about gametes, not the plants. If it is self-fertilized in the same flower, we have the male gametes and female gametes together. Okay. So from the male plant, we are getting these two gametes, these two chromatids, and from the female, we are getting these two. Okay. We are separating the gametes, just the gametes. Now these two gametes will form these. So it is easier to understand rather than that. Okay. So this is called Punnett square, Reginald Punnett discovered in this way, and that is easier for us to understand the whole process. Clear? And another thing is that tested the theory of inheritance of dominant traits using backcrosses. If we need to test the heterozygosity of a plant, we need to backcross or test cross the plant with the homozygous recessive, then we can only get that homozygous, that is the heterozygosity of the plant. We can determine that. Clear that one? Or I need to draw it again. Okay. Now, predicted the outcomes of genetic process, that is one representation, that is the Punnett square. Another theory is that called probability. Little bit math and stat. What is probability? What does it mean? The probability. If I toss a coin, so I can get either head or tail. Okay. If I toss a coin, what is the probability of having one head? 50%. How can you know that? We have only head or tail options. So we have two chances to get, and we can have only one chance to represent there, or the outcome will be only one, and we have more as a total two outcomes. So one of two outcomes we will get. That doesn't mean that if I toss a coin 10 times, I will get 50, that is 5 times head, 5 times tail. 10 times I can get head, no tails. Okay, so that means is it true or false? The theory, what we are targeting, the probability of having heads is 50%, probability of having tails is 50%. Is it true or false? True. Still true. But if I toss 10 times, I will get 10 head and 0 tail. Still it is true. Why? Theoretically, I am not getting that one. That is when I am doing the experiment, I am not getting that result. But it is still true. Why? What are we doing here by the terms of probability? What are we doing? If I will do it for 100 times, I will get 60 times head or 40 times tail. Still 6:4, not 50-50. If I do it for 1,000 times, I can get 3,000 times of head, 7,000 times of tails. Opposite. I'm not getting head all the times. Right now I am getting more tails than heads. If I will do it 10,000 times, I will get 5,555 times head and 4,455 times of tails. Very close at that time. If I do it for 100,000 times, I'll get very close to 550 and 50. So if I'll take more samples, then I'll get very close to 50-50, but not really 100%. So what are we doing here? We are predicting the chances. We are talking about the chances. That if you toss a coin, you can either have a head or a tail. The chances are 50%. But we are not getting that result. Then what should I do? If I'll get like the 10 times head or 9 times head and 1 time tails, if I get that 60 times head and 40 times tail, is that acceptable or not? We need to test that one also. There is another statistical test that what you are expecting and what is you are getting there, that is your observed and expected, whether your observed ratio is true or not, you can test that one also. And that is called the chi-square test. Okay. So the two things here. First is the transfer probability and second is the chi-square test. For the probability, this is the likelihood of an occurrence. Likelihood. that I can have that one. That is a chance that I can get that one, and at max I can get that one. But that doesn't mean it is all the time true, or each and every time I will get the same result. Okay. Generally, for that one in statistics, when we are doing the experiments, not only just genetic process. We are doing a lot of things. Okay. Suppose there are a patient, the smoking causes cancer. This is my hypothesis. So I took some people who didn't smoke, and I took some people who smoked. Couple of people of the smoking group, they have cancer. Couple of people of the non-smoking group, they also have cancer. So is my result true or false? If I can test these things and the test comes around the 95% time that there is a chance that people who are smoking having cancer, if I get that kind of result 95% time, then it is true. So I need not to think about 100%. If there is 95% chance, then it is true. And sometimes it is 95%, 99%, 99.9%, but not 100%. You will not get it any way in your result. In the reality, you cannot get it. There is no way. So this is one condition. You roll a die. The die has 6 faces, 1 to 6. Okay. If you roll a die one time, you can get any of these things, 1, 2, 3, 4, 5, 6. So if you think that you will get a 4 when you roll a die, what is the chance for that? Total outcome is 6. You can get any of the 6, 1, 2, 3, 4, 5, 6. And you are thinking about only one possibility, that is a 1, 4. So if you have the 6 total chances, you can get only one chance of 4. So the chance of having 4 in one roll is 1 out of 6. Total 6 chances, and we are getting 1, that is 1 out of 6. The probability is 1 out of 6. Okay, clear this one? So what is the probability of having 1 in one roll of die? 1 by 6. Any number I can get 1 by 6. Okay, that is my chance. If I roll the die again, second time, again the second time means it is not related to the first one. That first time I got 4, that means I don't expect the 4 this time. This is not true. If I roll the die again, this is totally independent. So I can get another 4 here also. So what is the chance of having 4 in 2 times? I roll a die first time, I will get a 4. I'll roll a die second time, I also want to have a 4. So what is the chance for that? This is called the multiplication rule. So the first time the chance is 1 by 6. Second time, if it is the second time, this is independent. So the first roll of die does not having any kind of implications or any kind of effect on the second roll. So this is totally independent event. Second time I can get that one, that is also 1 by 6. But in both cases, if I want to roll a die twice and I want to get 4 in each cases, that probability is 1 by 6 into 1 by 6. Is 1 by 36. If I do it for 36 times, that each and every time I am rolling the die twice, so I can have only one chance having 4 together if I roll the die for 36 times. That clear? So there are 2 things. First thing is that this is independent event. So my first roll of die does not have any kind of effect on my second roll of die. Independent event. So, and the condition is that and. If I roll the die twice, when I can get 4 twice and. Okay. First roll of die 4 and second roll of die 4. Then it is multiplication rule. You need to go for the multiplication. Okay. The second scenario, if you roll a die, roll 2 die, together, and you need to get either a 3 or a 4. But here also the same thing. If you roll one die, either 3 or 4. Either you can get 3 or 4. Now the condition is that when I was doing the first one, I was rolling 2 dice. Each and every time I could get a 4. If I roll one die, either I will get 3 or I will get 4. If I will get 3, I will not get 4. If I will get 4, I will not get 3. So what is the difference between these two? The first one and the second one? First one was independent. Each and every time if I am rolling a die, I am getting 4. There is a possibility that each and every time I will get 4. This time I am rolling a die, either I will get a 3 or I will get a 4. If I will get a 3, I will not get 4. If I will get 4, I will not get 3. This term is called mutually exclusive. So if you get 1, it rules out the possibility of getting other. That is called the mutually exclusive. If you are getting 3, you will not get 4. If you are getting 4, you will not get 3. There is no way you can get it. That is called the mutually exclusive event. And the word here, either or. Either 3 or 4. Either or. There was the term and. 4 and 4. Here the condition is either 3 or 4. In such case, we will have 1 by 6 plus 1 by 6. That is our total. And the chance is 1 by 3. Either 3 or 4. Because if I roll the die, I will get the 3. The chance is 1 out of 6. If I roll the die, I will get 4. The chance is 1 out of 6. Either 3 or 4, I can get any one of that. 2 out of 6, that is 1 by 3. Clear, these two? But generally in genetics, we will not do this one. That is the addition rule. Multiplication rule is very useful. Now a little bit more complex situation. Situation is that a person in your book, there is one example that one person in the dark family, they are having one albino child. Okay, so there were 3 children, and one is albino. 3 children, one is albino. Now the chances of that first child, so there are 3 events. What is the albino? Albino is something like that. You can do albino is a recessive gene. So the cross is something like that. In such case, in the Mendelian inheritance, we will get F2 generation like 3A and 1 small a in the F2 generation. If I do the same cross, or if it is heterozygous, something like that, we'll get this one as the F2 generation, and according to Mendelian ratio. So having one albino child from this cross, what is the probability? Probability of having one albino child from this cross. What is the probability? 1/4. And probability of having non-albino child is 3/4. Clear? Now if we go a little bit critical situation, they have 3 children. The first one is not albino, second one is not albino, third one is albino. That is one situation. In such case, what is the probability? 3/4 into 3/4 into 1/4. It could happen that first one is albino, second one is normal, third one is normal. It could be first one is normal, second one is albino, third one is normal. So if I say that what is the probability of having one albino child among three children, then I need to consider all these three together, all the probabilities together. Okay, and in such case it is little bit difficult, and for that one we use this form p plus q whole to the power n. So here is the probability, that one, the probability having non-albino child is A, having albino child is small a plus k. We have three children to the power 3. And the simple algebra. Okay? A cube plus 3a square a plus 3a square plus a square. That is the formation. And in such case, we use this Pascal's triangle. Okay? Anytime on this is cube, that is fine. If I'll go for more, 4, 5, 6, 7, 8, 9, whatever it is, we can use this form. And in this triangle, there are two things. The first one should be 1, and the last one should be 1, always. Okay? Now, if it is 2, when it is 2, that means the middle one is the total of upper 2. Okay? So in this case, this is 3. That means 2 plus 1 is equal to 3. This is 3. 2 plus 1 is equal to 3. Okay? Here 4. 3 plus 1 is equal to 4. 6. 3 plus 3 is equal to 6. 4. 3 plus 1 is equal to 4. And in such case, here is also. It is 15. That means 5 plus 10 is equal to 15. In this way, you can do, and if you use the algebraic expression, then you can get the a square, a cube, and other forms like this. A to the power 5, 10, a to the power 4, p is equal to 1. That is, actually the formula is something like that. If I do this cube, so the first one is 1 into then this is 3 like this. That means a square a. The next one will be 3 and the last one will be 1 with a 3 minus 3 and a 0 plus 3. That means it will become 0 and it will become q. And this is in your algebraic formula. But this is a complex situation, and in such case, we need to determine with this expansion. Okay, this is called the binomial expansion. Okay. Now, until now, we were talking about only one trait. Now we need to talk about more than one trait, more than one character. And that is called, if it is 2 characters, that means it is di-hybrid cross. Di means 2. So the first thing, we'll take the characters. The first character is seed shape. Second character is seed column. These are 2 characters. The first character is seed shape, second character is seed column. Traits for the first character. The first trait is round, second is wrinkled, For the seed color, the first trait is yellow and second trait is green. Okay. According to this one, we are taking round yellow seed in the first. Okay. Now take the genes also. For the round is dominant over wrinkled, so we are taking capital R. Wrinkled is recessive, so smaller. Yellow is dominant, capital Y. Green is recessive, small y. Okay. We are taking round yellow seed. Round yellow versus wrinkled green. Round yellow means for round, these are in homozygous condition. So 2 are yellow in homozygous condition 2Y. This is our round yellow genotype versus wrinkled and green. Pure round yellow versus pure wrinkled green. Okay, they are pure form. That means there is no heterozygous condition. Both the genes in homozygous condition, these are dominant, these are totally recessive. In some book, you can find a little bit combination of that one. That is round green versus wrinkled yellow. That is the study. But I prefer this one. Okay, pure dominant, pure recessive. What will be the gamete formation here? That is the main thing. First, what will be the chromosomal configuration here? In case of suppose anyone, what will be the chromosomal configuration? If you take a cell from there, you'll find the chromosomes for the green and suppose wrinkled green. How can you find the chromosomes? What will be the structure of chromosomes, or I can represent the chromosomes? Then I can have the idea of having gametes. What do you think? Say something. Like this. Is it true? There is one gene, RY. Okay. Anybody else? We are taking two characters, two traits. They are separate, so they are not in combination. Okay. Because we already said that there are two traits and there are two characters. So they are separate. That is the first one. So it is not RY. We will have two types of chromosomes like this. One containing R, another is Y in homozygous condition. This is our study, chromosomal configuration. If that is our chromosomal configuration, what will be the gamete for this individual? In one gamete, what will be the chromosomal configuration into this cell? Gamete, this haploid, it should be haploid. What will be the chromosomal configuration for this gamete?
R and a Y. One R, one Y.
Okay, so he's saying one R, one Y. Is it right or no? If I will say like this, what about that? Or what about that? If it is a diploid characteristics, these are haploid. This is haploid also. What about that? C right or I am right? Tell me, tell me. Clear? From your concept. Don't think that the professor is telling that this is true, that means this is true. Use your concept. This is haploid, sir. Definitely. Because only one chromatid is there, that is haploid. So this is 2R, 2Y, very easy to identify. And she is saying that no, that should be 1R, 1Y. Who is right? See? What do you think? Give some input. Don't just look at it. Give some input. Either it is right, either it is wrong. That doesn't matter. Give some input. What do you think?
But she's right.
She is right. Okay, tell me that she is right. What do you think? She is right. Why not me? Why I am not right? That is the explanation. What is the explanation for that? If you are right, what is the explanation for that?
You need one. If you have a wrinkled green seed, you're gonna need one. It's the wheel from the wrinkled side, one from the green side. Kind of.
Make it more clear. Make it more clear. You already did the meiosis class. Make it more clear.
When
What is N?
N is one.
One what? What is haploid? One means what? What is haploid? What is the term called haploid? And what is the term called diploid? That is the answer of this question. What is haploid? Yes.
One set of genetic information.
One set of chromosome. Only one set of chromosome. So this is one set of chromosome having two chromosomes together. The set, total set. I am not having any kind of set here. I am just separating the chromatids. So she is right. She took the one set of chromosome. That's why she is right. Okay, I am not taking one set of chromosomes. I am taking different chromosomes. Or I am just separating the two chromatids there. Okay. So she is right. She is having one set of chromosomes. So that should be our gamete. Clear? And this is the concept you have to be very, very clear about that. Otherwise, you will form like me, this kind of gametes. Okay? So we always think about one set of gamete. Yeah, very good. So from here we will have one set of gamete like this. From here we will have one set of gamete like this. So this will be our gametic composition of chromosomes. If we will have this kind of gametic composition, so two chromosomes, one is R, one is Y, and here are two chromosomes, one is small r, one is small y, in two cells. They will fuse together to form zygote. Okay? This R is allele of this one, Y is allele of this one. That denotes the traits. Okay? Traits are alleles. Characters are separate chromosomes. So they are alleles. If they will form the gamete that is one individual, so this should be our composition. Right? Because they are homologous chromosomes, they are alleles, they should be in the pairing, in a pair, or they should be in the pair. So actually our heterozygote will be like this. This is our actual heterozygote. What will be the phenotype of this one?
Yellow.
So the two dominant genes are there. One is round, which will suppress the wrinkle character. One is yellow, which will suppress the green character. So the phenotype will be round, yellow. Okay. Can you see the whole board from this side?
That's the computer.
Oh, okay. But anyway, just I'm trying to put it on top. So right now I have these individuals. I need to self-fertilize these individuals into F2 generation. Okay. What could be the gametic composition of this individual? What type of gametes this individual could form?
Could form a big R, big Y, a big R, little y, a small R, big Y, and then a little R, little y.
These are the four gametes this individual could form. Four types of gametes. Can you see up to this? Okay. Then I can do it here. Can I wipe this out? Is it okay for you? So we have four compositions here. Make a big Punnett square. Okay. Now do this by yourself. What are the phenotypes? This one. Round yellow. Okay. This one. What? Round yellow. Round yellow. Round. This one. Round yellow. Round green. Round yellow. Round green. Round yellow. Round yellow. Wrinkle and wrinkle, wrinkle yellow. So we can get total 4 phenotypes, total 4 outcomes. What are those? Round yellow. How many round yellows are there? Round yellow, round green, wrinkled green, wrinkled yellow, and a wrinkled green. How many round yellows are there?
5.
If you draw this diagram in this way, that is the gametes, you can, if you put the gametes in this way, this is very easy to find out all those things. Okay? All the round yellows. Look at that. All the round yellows are there. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 round yellows. Now, wrinkled yellow. Another trend. Wrinkled yellow. Look at that. All the wrinkled yellows are there. So wrinkled yellow is 3. Now round green. Another superimposed trend. These, and these. These 3. And wrinkled green, only one, the last one, the double recessive. So this is the ratio of Mendelian dihybrid cross. Finally, you will get 9:3:3:1. There. If you do the cross in this way, these 2 capitals on first, then the smalls and add capital, small, you can get this format. Always. So this is called dihybrid cross. So we are taking 2 characters. Each of every character has 2 traits. So there are total 4 traits, of which 2 are dominant, 2 are recessive. These are the full dominant characteristics and the hybrids having 9 ratios. These are 1 dominant, 1 recessive having 3, 1 dominant, 1 recessive, 3, and full recessive is 1. This is our total ratio of Mendelian dihybrid cross. Okay. Now the concept is that relate the principle of independent assortment. We knew the segregation of gametes. We knew that one, the segregation of gametes. Now we need to think about the independent assortment. What is independent assortment? We know the segregation of gamete, and as a result, segregation of gamete, we got a type of hybrid. This is our hybrid before. What is the segregation of gamete? That means each and every chromosome or each and every allele can have their possible combinations with other allele. That means this Y can combine with either of these 2 R's. This Y can combine with either of these 2 R's. That's why we have all these characteristics. So all the possible things. Now the probability of having R in this 4 set of things is 1/4. Right? Then that is another independent assortment. In the second case, the independent rule, that is having either only this Y or small y. These are independent event having 1/4 and 1/4 again. So having these 2 together is 1/4 into 1/4. Having these 2 together is 1/4 into 1/4. Multiplication rule of probability. That is the combination. Clear? And another thing is that here, what I will talk later in our next class. According to Mendelian inheritance, what we are talking, that the dihybrid cross means these two characters are located in two different chromosomes. Okay, otherwise this independent assortment is not possible. Okay, I'll give you one glimpse. Suppose there are two characters. Are you done with this one? I think so. Suppose there are two genes. One allele is AA and one allele is E. Dominant and recessive. Two traits. According to Mendelian principle, they are on the separate chromosomes. Like here is one chromosome and here is one chromosome. In such case, independent assortment is possible. All the possibilities of this chromosome with this chromosome with this one. Okay, that is independent assortment. If the situation is something like that, what will happen? Can we have all these kind of possibilities? Here I can combine this one anyway. In either way, or these two, like that. That is the independent assortment what it got. Is it possible in this case? Possible, but in a very few way, in a very restricted way. Think of this one. So in the first set of chromosomes, if it will isolate, we can have a gamete like this. These two chromosomes. In the second chromosome, these two, just like. And why? Why we can get this kind of all possibilities here? During anaphase separation, so we have the spindle fibers here. Okay, chromosomes are homologous chromosomes. They can be like this. So these two will separate in this way, that two will separate in that way. Okay, that we can have this type of gametes. If the thing is like this, it could be possible. There is high chance of that. It is just opposite. The chromosomes are these, because they are just rolled that way. In such case, what kind of gamete we will find? These two will go to that side, that two will go to that side. So we will have this combination, right? All four possible combination, and that is independent assortment. That is happening during meiosis. Which is happening during meiosis. Just the arrangement of chromosome during spindle formation. And that is the main cause of that one. What will happen for this? If we will form the spindle here, we will have only this combination, right? Only this combination. In such case, in one gamete, we will have this, another gamete we will have this, right? So that is not possible, that kind of combination. Still possible if we have a crossing over between these two. If we have crossover, then this will be one chromosome and this will be another chromosome. So the one chromosome will be, after crossover, we will find one chromosome like this, another chromosome like this, right? Okay. But crossover is rare. Rare means during meiosis crossing over is happening. But it is not true that each and every time the crossover will be between these two genes on. There are several genes there. So that means crossover is rare. the percentage of having crossing over between these two genes is less than 100%, not always 100%. Okay. So in such case, we will not have this gamete too much. These are the crossover types. We will not have these gametes too much. So the possibility of having these kind of offsprings will be less in the population. We will not have this 9:3:3:1 ratio. So what is the difference between these two things? There is only one short term. If you did genetics a little bit before, you already know that what. What is that? The difference between these two phenomena. Any input? That is called linkage. This term is called linkage. These two genes are linked by a chromosome, single chromosome. These two genes are linked by a single chromosome. According to Mendelian principle, two genes or two factors are not linked. That's why independent assortment is possible in proper Mendelian ratio. If the chromosome genes are linked, then there is only one chance, that is the crossover and crossover type, and the Mendelian ratio will not properly executed in that case. That is called the linked. We'll talk about this one later also. Now the question is that what I was talking about, that each and every time if I will toss a coin, I will get heads or tails, but 50% of heads, 50% of tails, but I got something like 7 heads and 3 tails. Is my result good or not? To test that one, we will do the chi-square test, which is called goodness of fit. How good is your result? How good is your result? That is called the goodness of fit. Okay. Then I can talk this one over. So here we are doing that Mendelian cross, dihybrid cross, and we are counting the probability that half is round, the probability, half is yellow in case of that one. So if I do the cross like this, round versus put the dust. To calculate the probability in Mendelian ratio, you need to do like this way. So if it is between RR and RR, just two genes, so we can have one this and one this. Probability of having one round is half. Probability of having one wrinkle is half. Okay. Then do the multiplication rule. Having yellow, that is the probability is half. Having green, the probability is half. If I separate these two traits, now having round and yellow, probability is 1/4. Multiplication rule. Probability of having round is half. Probability of having yellow is half. Probability of having round and yellow, multiplication rule, two independent event, we need to go for multiplication, half into half is equal to 1/4. Probability of having round and green, two independent events, and multiplication rule, half into half is equal to 1/4. So Mendelian principle, that is the independent, that is the sorting of gamete, follows the probability rule. Okay. Just this is too much math, I think so. Right? Now this is another one. So what we are doing, we are taking the purple flower versus white flower. This purple is dominant over white, and If that is the true, what we can get? So purple is dominant and white is recessive. We need to do the cross. In first F1 generation, we'll find this, that is the phenotype will be purple. In the second generation, we'll have these. So ratio between, okay, there is another thing here. If I'll do the ratio in this way, so capital P only 1, capital P, small p is 2, small p and small p is 1. Okay. This is called genotypic ratio. Genotypic ratio. In Mendelian ratio, this is in monohybrid cross. Genotypic ratio is 1:2, 2:2, 2:1. What is the phenotype? These two are purple and this is white. So purple is to white is equal to 3:1. Okay. If I do this kind of cross, I will expect the 3:1 ratio. This is my expected. So I have 150 numbers of plants. If I have 150 numbers of plants, how many will be purple? 150 divided by 4, how much? 112.5, and white will be 37.5. This is my expected result. Perfect 3:1 ratio. Okay, perfect 3:1 ratio. This is my expected result, that if I will do this cross, one pure purple with one pure plant, white plant, and if I will get 150 individuals total offsprings there, I will expect that 112.5 will be purple and 37.5 will be white. But that is not possible. Can I get the half purple, half white? I cannot get it. There is no way we can get it. But when we did the experiment, we got that result, that 105 is purple and 45 is white. Hundred five is purple and 45 white. What I was telling that if I toss a coin, I can get that kind of 7 is red, 3 is white. But I have to get 5 heads, 5 tails. Here is also we got 105 purple and 45 white. But we expected that this is our expected and this is our observed. We expected that we will get 112 purple, we got 105 purple. We expected that we will get 37 purple, white, and we got 45 white. Now the question is that what I got, is that result good fit with the expected? I need to calculate that. Can I accept this result? Okay, this is my good fit with the expected. To do this one, we need to do the chi-square test. Now, what is chi-square test? Is this X-like structure is called chi in Greek, chi. And chi-square is equal to sigma, that is summation observed minus expected whole square by expected. That means here we have two traits. One is, so sigma, first one observed minus expected, that is for the purple one. For purple one, we have observed 105 and our expected was 112.5. whole square by 112.5. Or I can for white, we have our observed is 45, our expected is 37.5 whole square by 37.5. This is our total. We have two traits. One is purple, one is white. For the purple, we have 112.5. That is our expected. We got 105. For white, our expected was 37.5. We got 45. Okay. So from here, we can get this is 0.5 plus 1.5 is equal to 2. So chi-square result is 2. That is our chi-square value. Now we need to find out the degrees of freedom. Degrees of freedom means how many characters we have. How many characters we have here? Purple and white, 2 characters. So our degrees of freedom is 2 minus 1, that is 1. Because why 2 minus 1? Why do we need to take n minus 1? Because if I have 1 character, I don't need to test anything like that. Okay, it will be 0. So always we need to take at least 2 characters to find out the degrees of freedom, and that is degrees of freedom is 2 minus 1 is equal to 1. And in your book, you will find a chi-square table. Okay. From that chi-square table, if you go to degrees of freedom, you will find all the probabilities. And according to the probability, we will find the probability is between 0.1 and 0.5. So this number, according to degrees of freedom 1, if you have the book, you can open that one. According to degrees of BF 1, this falls between 0.1 and 0.5. It is between that. Okay. What is the table number? Here the table number is also table 3.5. You can look at that book. Okay. Now 0.5 means what? 95%. 0.5 means 5%. Okay. So we are thinking that if it is within the 95% value, then it is good. If it is above 95% value, then it is not good. No significant difference. It is between 0.1 and 0.5. That means it is between 10 to 1 to 5% there. Okay. That means there is no such significant difference. If it is below 0.5 or above, I can say above 0.5. If it is above 0.5, there is a significant difference. If it is below 0.5, there is no such significant difference. If there is no such significant difference between these two results, should we accept the result or not? Yes or no? Clear this one? Later we have another thing that is called the student t-test, where we have to take the 5% chance, not the 95%. So it is saying that according to this value, it is saying that it falls between 0.1 and 0.5. That means there is no significant differences between these two results. If there is no such difference between these two results, then we can accept this. So this is true. If it is above 0.5, if it is 0.6 or something, that means it will indicate that there is a significant difference between your observed value and expected value. If there is a significant difference between observed value and expected value, then we cannot accept that result. And the chances are 95%. we need not to think about 100%. If it is very close to 100%, that is 99.9%, your result is very good. Your result is very good. Clear? Little bit math. Yes.
How do you decide to use the t-test over this test?
Okay, that is a good question. T-test means when you are targeting two types of population, one is control, another is experimental population. Okay, two types of population. So suppose in smoking cancer case, I have some people who didn't smoke and some people who smoked, and we have the cancer percentage between these two. So in such case, if I need to test that one, I will use the student t-test because there is no such expected result there. There is no such expected result. I am just targeting the difference between, we got some differences, whether that differences is significant or not. Okay? Yeah.
If you wanted it, 1.5 to 50%, 195, or 0.05.
0.05. So yeah, actually up to 95% we can take that result.
So you want P less than 0.05 then?
Yeah. So up to 95% we can take the result. In case of student t-test, above 95%, if the difference is above 95%, then we can take the result. In this case, if the difference is within 95%, then we cannot, we can take that result. And the thing is that this is qualitative. So we have some expected characteristics and we have some observed thing, qualitative. In case of student t-test, there is not qualitative, that is quantitative. Okay? I think this is all about this part. I'll check the sampling. I'll give you some kind of problems, okay, based on this monohybrid cross. And I will suggest you do one chi-square problem. So I will give it as a homework, one chi-square problem and a couple of monohybrid and dihybrid cross problems. So do the process, practice it. I want it to put in your brain this one very clearly because later we have a lot of different things. That is epistasis and other things where the Mendelian ratio is not following. Okay, so to understand those things, you need to understand this one first. Very well. So I will give you some kind of problems here. You can submit it. You can submit it. So I can give you some kind of problems in Canvas within a couple of days. Tomorrow or Saturday, I will post that one.
Do we then bring it into class with us, or are we gonna submit?
I think this is you need to do it by hand. So whatever if you prefer, that is fine. If you want to scan it and put it by digital form, that is also okay. You can bring it in the class and give it to me. That is okay. But I just want you to practice some problems. Then you can have a very clear idea about monohybrid and dihybrid cross. Okay. If you do not do the problems, it will not be easier for you to understand. You need to do it by your own hand. That's why I told you to do that table by yourself, not just copy. If you copy that one, you will not understand. Yeah. Yeah, I'll send you one email that I posted that these problems in Canvas. I was thinking after the six-linked inheritance, when I am done with the six-linked inheritance, I'll do that. But I think just a couple, 2-3 problems, 3 or 4 problems, something like that, with the monohybrid and dihybrid cross. And do the cross property. Okay. So you need to indicate the parental generation. You need to indicate the F1 generation, F2 generation. You need to indicate the gametes there and their phenotypes. Okay. If I will ask for your genotypic ratio, you need to show the genotypic ratio. If I ask for the phenotypic ratio, you need to show the phenotypic ratio. Okay. Any question about these things? I think this is a little bit complicated, but I have been. And the probability part, I will not do too much on the probability part. You just need to understand that how the probability, theory of probabilities occurring here into this dihybrid and monohybrid cross. Just go through that part in your book and just one time, that will be fine. I think so. Any question? Is your head spinning? Yeah, you can submit. Just put your name there. Yeah, better. Yeah.
He wants to turn in his meiosis.
Yeah. Okay, so we are done for the day.